Okay, section 19.4 is about voltaic cells. It could be labeled electrochemical cells, which is a more general term, and we'll go over all of that. So up until now, we've seen redox reactions that occur with the electrons being directly transmitted from the reducing agent to the oxidizing agent. If I take a piece of zinc and drop it in a beaker containing copper solution, the copper plates directly onto the zinc as the zinc dissolves into solution, and the electrons are transferred by physical contact between the reactants. We can, however, physically separate the reactants and connect them with a wire and force the electrons to travel through that wire in order to perform the redox reaction. And we can even force them to do electrical work on the way. So as the electrons want to leave the reducing agent and go do their job of reducing the oxidizing agent, we can force them to, say, turn a motor or heat up a heating coil or something on their journey from reducing to oxidizing agent, which is pretty nifty. This is how an electrochemical cell works. So electrochemical cells come in two varieties. So there is a voltaic cell or a galvanic cell. So Volta and Galvanus were two people that were studying these sorts of reactions and cells, and I think Volta is the one who was a better marketer, because we call these primarily voltaic cells instead of galvanic cells. But they are the same thing. They are cells which use a spontaneous chemical reaction in order to produce a voltage and a natural electron flow. There are also electrolytic cells. Electrolytic cells will utilize a chemical reaction which is not spontaneous, that won't naturally occur. But if you hook up an external source of voltage, like say another battery or a generator or something, then you can force these non-spontaneous reactions to proceed anyway. So they drive the electrons against their natural flow in order to achieve, the whatever electrochemical product you want. So these voltaic and galvanic cells are batteries. When they are discharging, they are operating as a voltaic or a galvanic cell. An electrolytic cell would be something like a battery that is being recharged by application of an external voltage or driving the electrons against their natural flow and recharging the battery, or other applications like electroplating. You can cause metal cations to plate onto a surface, forming solid elemental metal, for reactions where that is not a spontaneous process, well, you can drive it by applying an external voltage. And so electroplating is an example of an electrolytic cell. And your lab that you're not doing, but that you're watching someone's lovely video about, is going to explore both types of these cells. So you may recall from all the way back from chapter 4 that all the different metals have different reactivities, and table 4.7 shows what we call an activity series. The metals, hold up, it's a little small for me. The metals near the top are most easily oxidized. These are things like aluminum or manganese. They could have put sodium and potassium on there, which are, among the most easily oxidized. And those metals will readily give up their electrons to turn into cations. And then conversely, you can see how the ions also have an activity series. The the cations that correspond to very active metals like sodium plus ion, potassium plus ion, aluminum plus ion, magnesium 2 plus ion. These are ions that are very stable. They do not readily accept electrons, but down at the bottom, something like a gold ion or a silver ion, they are very chemically active and they will readily accept electrons and be reduced to form their elemental metals. So let me get rid of that real quick. Actually I need it up again. I apologize. So looking at this activity series, we can tell which metals will pair spontaneously to make a voltaic cell. If you pick a metal from the top of the activity series and pick a cation from near the bottom of the activity series, then the oxidation of the metal and reduction of the cation are going to be favorable. So for example, we could pair zinc metal with copper 2 plus ions, and that will form a voltaic or galvanic cell. Anytime, it doesn't have to be top or bottom, anytime the metal is above the ion in that activity series, you'll get a spontaneous reaction. If I were to pair silver metal with those copper ions instead, then that would be a non-spontaneous reaction. The copper ions would not naturally reduce to form copper solid. This would have to be driven by an external electric voltage, and so it would be an electrolytic cell. Okay, and I'm actually going to leave this slideshow viewer up, and I'm going to trade which slideshow I'm looking at. All right. So figure 19.4 shows a simple example of a voltaic cell. This is a maybe impractical way to build a battery. The batteries that we use every day, like AA batteries or lithium-ion batteries, have been engineered to be safe and small and reliable, but this version of a voltaic cell is really useful for teaching, and it was in fact the first types of voltaic cells that were ever developed. And so we have here two beakers that are going to contain ion solutions on the, hold up, I'm trying to figure out if your picture is reversed or not. It's not reversed. On the left side, you'll have a solution of zinc 2 plus ions and a bar of solid zinc metal. And this is where oxidation will occur. The zinc metal will give up its electrons and produce zinc 2 plus ions. That zinc metal bar is called an electrode. And then there is a wire which connects the zinc to the copper bar on the right side. That copper bar will receive the electrons and pass them onward to copper 2 plus ions in solution, reducing them to generate new copper solid on that copper electrode. That's where reduction occurs. And so the solutions there containing the ions, the zinc concentration will increase over time as this cell is run, and the copper ions will decrease in concentration as the cell runs. So there's a couple more important and interesting things about this example of a cell. So first of all, if a solid reactant is not a part of the chemical reaction, then one or both of the electrodes can be made of any conductive but chemically inert material, such as graphite or platinum. So in other words, we don't really need a big bar of copper over on the right side. We could have a platinum bar or a rod of graphite. What would happen is copper could plate onto that platinum or graphite just fine, because solid copper is not actually a reactant in this cell. It is a product, and so solid copper isn't required at the beginning. The zinc, however, in this case is required. We would need to have that solid zinc electrode. There are some reactions where we will reduce a cation, say from the 3+ state to the 2+ state, and there's no solid metal involved at all. And in that case, also a platinum or a graphite electrode would work fine. Now the zinc electrode is right here. The zinc electrode is where the oxidation occurs, and so we call it the anode. Let me erase this up here. Let's see how clever I can get about things. So here's the anode on the left side. Yeah, that wasn't very well aligned, but that's okay. So anode can refer to the zinc electrode itself, the bar of zinc metal, or it can refer to that whole half of the cell, the zinc 2+ solution together with the electrode. And then the cathode is the name of the electrode where reduction occurs, or that copper electrode, or again, the entire right side of the chemical reaction, the copper side of it. So anode is where oxidation occurs, and anode and oxidation both start with vowels. That's a good way to remember which is which. Cathode is where reduction occurs, and the words cathode and reduction both start with consonants. So that's a good way to remember those. The cathode is also got a T in the middle, and that's T looks like a plus sign. So cathode is what we would label as the positive side of a battery. Also, obviously, cation, cathode, and positive side of the battery, they're all related. Cations are positively charged. The anode would be the negative side of a battery, just like anions are negatively charged. And if you have an electrolytic cell where things are kind of a little bit backward because it's written in the non-spontaneous direction, I just want to assure you that the cathode is where reduction occurs for an electrolytic cell or for a voltaic cell. It's the same in either case. It's very easy with redox chemistry to get confused about these different standards, and so I would just encourage you to find some way to make sure that you always get it right. And I recommend cathode, reduction, both starting with consonants. Whether it's a voltaic or an electrolytic cell, reduction always occurs at the cathode. Oxidation always occurs at the anode. So there's another feature here. You can see connecting the two beakers is a salt bridge. And a salt bridge is a really interesting but necessary part to the voltaic cell. So let's do a little thought experiment. If you have oxidation occurring at the anode, then zinc 2+ ions are accumulating in solution. Eventually that solution is going to no longer be neutrally charged. You're getting positive charges added to it, and there's nothing to counterbalance that. Eventually that anode is going to be positively charged overall. And for the electrons to leave the anode and travel over to the cathode, they're going to be pulled back by that positive charge in the solution. Eventually the solution will become so strongly positively charged that electrons will no longer be able to leave and the reaction will come to a stop. We can look at the cathode in the same way. The cathode is going to be losing copper ions in solution, and so that beaker will become negatively charged. And as it becomes more and more negatively charged, the electrons are going to begin to be repelled by the cathode. And the electrons can't travel to the cathode if that repulsion becomes powerful enough to stop them. And so without a salt bridge, both the anode and the cathode solutions would eventually build up a strong enough charge to stop the reaction, and the battery would die prematurely. So what a salt bridge is is it's a connection that has a semi-permeable membrane, ideally that would not allow those metal cations to pass in either direction. But it is filled with some inert salt, like maybe potassium nitrate. And that inert salt, those ions are allowed to pass through the salt bridge and into the two beakers on either side. And so as zinc ions are accumulating in the anode, if your salt bridge is made of potassium nitrate, then the anions from your salt bridge, the nitrate ions, are going to actually physically flow and migrate into that anion beaker. And they do that in order to counterbalance the charge. They are attracted by the new positive charges of the zinc, and they go counterbalance it, and that allows the anode to remain electrically neutral. Similarly, as the copper ions are lost on the cathode side, the cations from the salt bridge, perhaps they're potassium, those cations will migrate to the cathode, and they will replace the copper cations that were lost and allow the cathode to remain electrically neutral. So the salt bridge isn't a part of the redox chemical reaction, but it is an essential component for an operating voltaic cell. And we can think of the salt bridge as allowing the electrical circuit to be completed. Let me turn that off for a minute. Okay, so if I have the anode and the cathode, and there are electrons flowing in this direction, that is not a complete electrical circuit. Electricity cannot flow unless the circuit is complete. And so over on this side, we'll have the ions from the salt bridge. I guess technically, let me be a little bit more clear here. We're going to have the anions flowing this direction. Anions flow this direction, and the cations flow that direction. Okay, sorry about that. And this flow of anions represents electrical current. We're so used to thinking of electrical current as the flow exclusively of electrons, but really any flow of charge is electricity. And so by having cations flow this way and anions flow that way, that creates an electrical current which completes the circuit and allows the battery to function. So let me pull this back up again. So as you see, the chemical reaction in a voltaic cell is physically separated into two parts. We call them the anode and the cathode. We can talk about the chemical reaction itself as being separated into two parts as well. Each of them are called a half reaction, and each of the physical parts of the cell are called a half cell. So each half cell, which contains half of the chemical reaction, say the oxidation of zinc in the anode half cell or the reduction of copper in the cathode half cell, each half cell will have its own electrochemical potential or voltage. And it's the combination of the electrochemical potentials or voltages of the two half cells that will give you the voltage of the voltaic cell overall, or the battery voltage. And we'll cover that in the next section, how to handle that mathematically. But by separating the two parts of the reaction serves multiple purposes. First of all, it allows us to force the electrons to travel through a wire. They cannot actually reach the copper 2+ ions unless they travel through the wire, because the two half cells have been physically separated from one another. It also means that these half cells are somewhat modular. You could take your copper half cell and replace it with some other metal, silver, iron, any metal you can imagine. You can replace the copper half cell with that other half cell, and you would have a new battery with a new voltage. And again, your lab was going to sort of explore different combinations of anode and cathode half cells and the voltages that they may generate. So I'm going to erase all of this. It's kind of a funny video because you just see my head up here, but it's obviously really tedious to represent a voltaic cell by literally drawing these two beakers and drawing the electrodes. And so we want a quicker way to represent a voltaic cell. But writing the balanced chemical reaction is also a bit tedious and not particularly helpful because that separates things in terms of reactants and products instead of organizing them naturally in terms of their half cells. And so we have another notation which is called cell notation, which is like a really simple map of how a cell is actually constructed. The way to do cell notation is to start with the anode and just kind of work through the different phases of matter or the different components of your voltaic cell until you get to the cathode. In this case, our anode is zinc solid, so we will write that. Zinc solid. So that is the anode. And then we'll draw a vertical line, and that vertical line represents a phase boundary. There's the zinc solid and then a phase boundary to the zinc 2+ aqueous solution. And I'm going to go ahead and say it's a 1 molar aqueous solution. That would make this a standard zinc half cell. Then we're going to draw a double vertical line. That double vertical line represents the salt bridge. You kind of have one boundary on the anode side and one boundary on the cathode side. So that's the salt bridge. Now we're into the cathode solution, which contains copper 2+ ions in aqueous solution. And if this is a standard copper half cell, then they are in a concentration of 1 molar. And then lastly, the cathode itself, the copper electrode, Cu solid. Okay, so you can see how this contains all of the essential elements of the voltaic cell. It's much simpler than either a complete balanced chemical equation or a actual drawing or schematic of the voltaic cell itself. You can see what metal is oxidized on the anode, what sort of cations are reduced in the cathode, and it's just really quick and easy. So let's switch to PDF. Okay, so let's write the cell notation for a voltaic cell that is made from the reaction of copper 2+ ion, of silver 1+ ions with copper under standard conditions. The silver plus ions would coat themselves on a piece of copper metal as the copper dissolved if we were to place them in the same beaker. But instead of putting them in the same beaker, let's construct a cell out of them. So we'll want to separate the anode from the cathode. What is the anode in this case? It's where oxidation will occur. So that is the copper solid going to copper 2+ ions. And I never said that it's going to form copper 2+ ions. And so I suppose you could argue with me on that point. But we've seen enough copper redox reactions at this point, I hope, that that copper 2+ ions are maybe something that you've intuitively thought of. So we'll have copper solid, copper 2 plus. And it's aqueous at 1 molar concentration. That is the anode. We'll put the salt bridge, and the silver plus ions are aqueous, the concentration of 1 molar, and they are going to be reduced to form silver solid, and that is the cathode. So it says to draw a diagram of the copper and silver cell and to identify certain components to it. So I'll draw the anode first. I'm going to draw 2 beakers. This is the anode that contains a block of solid copper metal and a solution of copper 2 plus ions. And they're going to be connected by a wire to the cathode that has a big rod of silver metal and silver plus ions in solution. And then I will also draw that enigmatic but necessary salt bridge. There it is. And I'm supposed to identify the cathode and the anode. So this is the cathode. In other words, this is the positive side of the battery. This is the anode, or the negative side of the battery. Show the flow of electrons. Electrons will flow from the anode to the cathode. And the flow of ions. So copper is going to be generating copper 2 plus ions. Silver 1 plus ions are going to be plating onto the silver. And then it says to assume that the salt bridge contains potassium nitrate. So remember that the potassium plus ions are going to flow into the cathode, and the nitrate ions, the anions, are going to flow into the anode. And so that is a diagram showing the voltaic cell that is formed from the oxidation of solid copper and the reduction of silver plus ions.